Welcome everyone. My name's Michelle Brunzleski, and I'm the Global Marketing Manager here at Control Station. I would like to thank you for the privilege of your time today and joining us for our public webinar series. This webinar is called Hijacked. 3 questions to determine if your tuning software is ready for the real world. With me today, I have Dennis Nash, the President and CEO of Control Station, as well as Brett Beauregard, the Director of Product Development. Okay, we're just going to go over a few things about Control Station. We have been around for 34 years. It was originally founded in 1988 at the University of Connecticut. We partner with our customers to solve their process control needs using a combination of world-class software and expert services. We are proud partners to 1 out of 2 manufacturers listed in the Fortune 500. We have a global footprint. We have offices in the United States and Ireland and have successfully deployed our solutions to support facilities located in over 70 countries and still growing. Today's agenda, we're going to go over what it means to be hijacked. Then we're going to go over what is steady state versus non-steady state modeling. Then we're going to go over 3 questions to clarify the difference. We're going to do a summary and then questions and answers at the end. On your toolbar, you will see a box called questions. If you click on the pane and open it up, you can type in your questions there and we will address them at the end. So with that, I would like to hand it over to Dennis Nash. Dennis.
Good morning, everyone, and thank you, Michelle. Judging by the sign up for today's webinar, there are plenty of practitioners who are probably familiar with this scenario. The dynamic behavior of a typical production process is anything but clean and simple. Seemingly crazy or erratic behavior is unfortunately commonplace. So when you as a practitioner see this, the following experience may be familiar. Your task is to take that control loop, which has been identified as being excessively variable, which is damaging your productivity, your quality, and to tune it. When you launch your PID control loop tuning software, however, the software stipulates that the process variable, the PV, must be held quiet or at a steady state before commencing your bump test. And that's when a familiar experience comes to mind, because that's not how software is supposed to be. Since the first PID tuning software was introduced, the purpose of the software was to make PID controller tuning simple. Software as a general product category, it seeks to automate repeatable steps. It seeks to facilitate good and effective decision making, but also, and maybe most importantly, software for PID tuning was intended to tackle the difficult task that the everyday practitioner may know or maybe may not remember because they don't tune loops frequently. With PID tuning software, the primary task has always been to accurately model challenging dynamic behavior, that type of behavior which is typical of everyday industrial environments. Unfortunately, that has rarely been the case. Tuning software routinely fails this most basic and expected requirement. As our head of product development, Brett Beauregard, knows quite a bit about this challenge. Brett, please provide some background for today's audience.
Sure, Dennis. Morning, everybody. So I'm Brett Beauregard. I'm the Director of Product Development, and as Dennis said, I spend a lot of time working on steady state versus non-steady state and trying to make our products really be able to handle the difference. So when we talk about steady state, mostly we're talking about what you would think of, right? We're talking about a calm ocean, right? Everything's moving comfortably and steadily, no major variations, maybe a few ripples here and there, but everything is calm. So the controller output is calm, the controller input is calm. We're not seeing any major upsets and things like that. There's an added stipulation when it comes with, or an added kind of wrinkle that comes when we're talking about process dynamics. So when we're modeling dynamics, changes, deviations from the norm, and things like that. And one of the things that kind of misses sometimes, or one of the things that we include in our definition of steady state, is that we want to see changes in dynamics. So you were thinking of a calm ocean, but if you have something like a tank level that is steadily rising continuously, we would classify that as dynamically steady. That is a steady condition. Everything is at equilibrium and calm. There's nothing kind of different happening, knocking you around. That is a steady process dynamically. Now, if you contrast that with non-steady state, also something that is probably familiar to most people, here we're talking about a process that's undergoing a variety of changes. So it's not a calm ocean. It might be a storm. We have ripples that are occurring due to external impacts that are coming possibly and changing us. We have ripples that are occurring due to set point changes and things where we've changed. We have ripples that are occurring due to load changes, and maybe even due to some mechanical issues and things of that nature that are all causing our process to not be steady. So when we're talking about, when we say steady state or non-steady state, these are the differences, right? We're talking about a calm process dynamically, or a process that's got some motion into it. So that's the difference that we're trying to highlight when we're talking about these things in this presentation. Dennis?
Thanks, Brett. So as Brett just noted, today's webinar will focus on a common failing of controller tuning software products. We've entitled today's session Hijacked, as certain software vendors claim the ability to accurately model non-steady state process conditions. Their use of non-steady state as a feature only applies in the simplest of applications. To be blunt, their claim is intellectually dishonest. Most software packages fail to model and tune complex process conditions, what today's audience knows as the real world. So how can practitioners in plant management determine if a tuning package is truly capable of handling those real world conditions? How do you know if an investment in software will provide the necessary value? How can you be sure that you too aren't being hijacked? Today we'll explore 3 separate questions or scenarios that provide clarification. Our first question relates to integrating loops. These loops are exceptionally commonplace in industrial applications. Think of level control as an example, one that Brett mentioned earlier in his remarks. As it relates to non-steady state modeling, it's essential to know if the software can accurately model such a basic process using closed loop data. Michelle, let's learn some information from our audience.
Absolutely. I am going to pull up a poll. And you should see it on your screen in a minute. And all you have to do is take your mouse and click what applies to you. There's only one option. Do you have integrating, example, non-self-regulating control loops at your production facility? Yes, no, or I'm just really not sure. So I'll give everyone a few minutes to answer this, and then I will close it and share the results. Looks like we have about half the vote in. All right. I'm gonna close it. Close and share. Here we go. Here are the results. So 75% of you say yes, that you do, and some of you just aren't sure. So with that, I'd like to hand it back over to Brett for the answer. Brett.
The answer is yes, probably. For those of you that are not sure, the answer is that probably you do have integrating processes. So an integrating process, here's an example of a pumped tank level. So you might have a surge tank or some sort of production tank. So an example here of a tank level is, or of an integrating loop here is, it's one where the output controls the rate of change of the process. So here we can see a tank level of some green fluid, whatever it may be, and we have 17.8 going in, 17.8 going out. This level is constant. But if I were to open or close the controller valve at the bottom there, we would see that the outflow would change and that tank level would just rise or drop steadily in one direction. So this is an example of an integrating process. So as an example here, right? If we move, we have one balance point where the flows are equal, but then if I increase the output, it may drain to the bottom, or if I decrease the output, it may raise to the top. So this, at first blush, and by a simple definition, you might consider this to not be steady state. This is kind of descent into zero. But here we have what I would consider, and by our definition during this thing, we have two different steady states where we have two dynamically steady. I guess there's a third one there at the end where we are steadily cavitating the pump for 7 minutes. So hopefully the operator is getting disciplined for that. But this is an example of an integrating process. So here we have a steady state bump test that you could use to generate the information you need to get controller parameters for. This is a open loop step test where we change the controller output to below the balance point of 70 and then above the balance point of 70, and then we observe the two resulting slopes. So this is what some vendors would consider a non-steady state model, modeling this data. This is non-steady state data according to some vendors. And based on what we talked about a little earlier, I don't think we could say that this is a, stormy ocean. This is a very calm sea, and we're just going in two different directions. So dynamically, when we're talking about process dynamics, which is what we talk about when we're talking about process control, we have one steady state, another steady state, and you're doing the modeling of these behaviors. So this is a test and also an example of an integrating process. This is what some vendors would classify as a non-steady state test. Let's contrast this with what we're talking about when we talk about a non-steady state test. So here I have a screenshot of a model fit on our software. We have the controller output in the bottom half of the trend, the process variable and set point on the top half of the trend, and then we have our model fit on the this yellow line over the data. So here we can see what I would consider, and I hope that those of you on this call would also consider a true non-steady state condition. So here we have a level loop in automatic mode, adjusting the output, and we are observing this kind of undulatory non-steady state response. You also notice that there at no point during this test has the process been steady or flat. We have consistent dynamic changes, and we are observing a good model fit of a true steady state. We can also see the model that we've created. We've identified, in this case, a 4-minute dead time, which this is separate from this presentation, but identifying long dead time loops is also a strong feature of of our modeling. But obviously, this is far more complex, and this is what we mean when we are talking about non-steady state modeling. So this is the first question, right? And this is the answer. Can your software model this closed loop integrating data? My guess would be that the answer is no, unless of course you're using our software already. Dennis?
Thanks for that, Brett. Our next inquiry involves non-integrating processes, otherwise known as self-regulating processes, as another very common type of process. By determining if PID tuning software can support non-integrating loops, we learn a lot about the software itself. Michelle, what can today's attendees tell us about their experience with non-integrating loops?
All right, let me pull up the next polling question. You should see it on your screen in a minute. Again, as once before, just take your mouse and click what's ever appropriate to you. Do you have non-integrating, example, self-regulating control loops at your production facilities? Yes, no, or you're not sure. So I'll give everyone a few seconds to vote on that. We only got about 40% of the vote in. Let's shoot for 60 or 70. All right, that looks good. I'm gonna close it. And we'll share the results. You should see the results on your screen in a minute. 80% say yes, and 20% say they're not sure. So with that, we hand it back over to our expert, Brett.
All right, so here I obviously have to make a joke about if you said no to both. You probably got one or the other. Generally, there will be at least one or two of both types. So the most common loop that I have encountered in my travels is this type. So you'll have integrating processes and level loops and things of that nature. But in my experience, maybe 80% of the loops at a typical production facility will be of this type, non-integrating. So here, these are ones where if the tank level or the integrating process is one where the output determines the rate of change of the process variable, a non-integrating or self-regulating process, as they're also called, will determine where you wind up. So you have an output. For every value of the output, there is some input to which you will achieve some kind of steady value. So we change the output from 140 to 150, we will see some change and some kind of tapering out of the data. So this is an example of a self-regulating process. We have a heat exchanger with a warm liquid flowing through the center, which we are then cooling with a control valve to the left. The PID controller is opening and closing this valve based on the exit temperature. So it is adjusting the amount of cooling based on what it's seeing on the exit temperature. For every value of the control loop, if we were to put this in manual, for every value that or every position of that controller output, we would have some kind of steady exit temperature to which we would apply. Okay, so in this case, steady state means what you think steady state means, right? It's dynamically, it's going to be perfectly flat data. So here we have an example test of this process where our manual open loop tests where the controller output is held at one value and then stepped to another value. And we can see that the process data starts at one steady state and cruises up dynamically and then tapers out at some new steady state. So a heat exchanger is one example of this type of process, but it could also be a flow or most pressures. Even if you think of your car, it behaves in this way, right? We change the gas pedal angle and it changes. So this is probably the most simple test that you can perform. So we have a open loop test. There's no controller in this. We make a step. We go from one steady state to another. So most software products require that at least some of these conditions are met. So some of your lower end soft tuning packages will require that you can never be in automatic mode. You have to be in, you can never be manual or automatic mode. You have to be in manual. Some require that you have to start and end at steady state, but also most importantly, all of them, other than the one that we're talking about here, ours, require that you start at steady state. So starting at steady state is a requirement of most software packages. And again, we will contrast that with data that we can model, right? So here we have another screenshot. This is of a different type of data, right? So instead of being a level loop, this is data from that self-same heat exchanger. No, this is actually from a different heat exchanger. But we have the output on the bottom, we have the process variable on the top, and then the yellow line is our model fit. As you can see, steady state is relatively absent from this data set as a whole, and also from the initial condition. We have a very drastic and changing initial condition, and the model fitter is not confused by this. So the benefit here is that this data is much more realistic. Okay, so this is data that you would expect to see. By not requiring that the loop achieve a steady state before you do your test, it's much more likely that you will be able to do a test. Right? The joke is, if I could get it to steady state, I probably wouldn't need to tune it. That isn't always true, but that's the idea is, okay, let's tune this loop. Okay, first thing we have to do is get it perfectly flat, and then we can start our test. That may be realistic in some cases, but it's much nicer if you can just say, all right, wherever the loop is right now, we can do a set point change. There's our data. Right? So there's many more opportunities for finding good data. I should also add, on the screenshot, you can see that we have the data within 2 vertical bars. And those vertical bars can be moved. So that's also helpful if you've started a tuning session or you have a file that has a long stretch of data. We can zero in and get really small sections of data. And because the non-steady state requirement is not necessary, right? There's no need for non-steady state data. It's much more likely that you'll be able to find a good spot that really indicates the dynamic behavior of the process. It's very powerful. It's a very powerful tool. And yes, just the final joke here at the bottom. If you could establish steady state, I mean, getting to steady state is already the goal of tuning. So, that's probably, it's nice that you don't need to get it to steady state to then try to tune it to get it to steady state. Dennis?
Great input there, Brett. Which brings us to our third question. As shared at the beginning of today's session, oscillatory, noisy conditions, they are indeed the real world. Learning if a vendor's product can handle these commonplace conditions reveals the software's true worth. Michelle, let's ask our audience one last question about their experience with highly dynamic conditions.
Will do, Dennis. All right. You should see the polling question in a minute. Do you have control loops that demonstrate noisy, oscillatory, dynamic behavior? Yes, no, or you're just not sure? So I will leave this open. Oh, people are responding quickly. Fantastic. All right. A few more seconds, and then I'm going to close and share. All right. All right, I'm going to share the results you should see on your screen in a minute. 83% said yes, and 17% said they're not sure. All right, Brett, back to you.
I am not surprised that people in a webinar about loop tuning have a lot of oscillatory loops at the plant. This is really common, right? Oscillatory happens. It can be the result of many things, and it makes your life really difficult. Here, we're talking about straight up oscillatory processes. So there are the processes that we've kind of been discussing where it's hard to get it to steady state, or it takes a while, or it's balancing on the head of the pin and then it gets knocked away. But then there's loops that are just oscillating. Doesn't matter the time of day, doesn't matter where you're living with, it's just oscillating all the time. This is very difficult because it's very difficult to model and tune these because a lot of times these loops are some of the most important loops in the plant. So the idea that you could say, all right, I'm going to put this loop in manual and do a test might get you kicked out of the control room. So that's that these can be very, very challenging. So these oscillations can be the result of a variety of effects. So the controller might be poorly tuned, the process may be nonlinear, there may be some mechanical issues you're dealing with, there may be some load changes that are causing these oscillations. But the fact of the matter is, you really want to address these things, because unless in the very, very rare case that they are related to the process itself, there are a few processes that actually require these dynamic changes, but almost always it's just a problem. It's just increasing wear and tear on your equipment, causing variability in final product and things of that like. So it's definitely something, it's almost always something you want to get rid of. And this is a challenge to tune. As I said, finding a good test is nearly impossible in automatic mode. Putting it in manual mode is not an option. And here we can see that if we have a comparison, same data, steady state modeling versus non-steady state modeling, you can see that the steady state modeling does its darndest, but just because it is incapable of looking at, the true dynamic behavior of the process without a steady state to work off of, it just can't do a good job. Whereas if you look at the non-steady state modeling, it kind of doesn't fit as well at the beginning, but it does a better job towards overall because of approximating the dynamics, because it is not impacted by the initial steady state. Okay, so that's a good thing. So then if we contrast that with probably my favorite screenshot in the history of Control Station, I love this. It may look like it's fake, but man, this was a wonderful, wonderful test. And it's not all that uncommon. This one's just a screenshot that we have that I see every once in a while. I love it. Okay, so here we have oscillatory data. This is it is a temperature loop, I believe, in a boiler. Okay, critical, oscillatory, probably oscillatory due to some nonlinearity where it's present, where the loop kind of, it's aggressive in one direction, conservative in the other, and the loop just kind of causes this this oscillation. You can see that both the PID output and the PID input are fully oscillating. You can also see that the red line is a set point change. So even in the middle of this, we just said, all right, let's do a closed loop, automatic. We'll change the set point up, down, up. And that is enough dynamic information or enough change to lock in a great model fit. You can see that yellow line is a fantastic model fit of this process data. So this is true non-steady state oscillatory data, and this is not uncommon, just a really kind of powerful, a really powerful fit. And frankly, what I think people expect from tuning software is that they can just put whatever data is coming from their process into the software and get it, right? This last point is very, kind of very poignant. It's the software's job to help you deal with these oscillations. It's not your job to smooth everything out so that the software can help you a little, right? If they can do this job, it can make your life much more easy, at least in this respect. I think there's still a lot of stuff that you're going to have to deal with, but hopefully tuning isn't the problem. Okay, so this kind of wraps up the three cases, right? So we can see this is temperature. So oscillations in integrating processes or closed loop, the first question, can you handle closed loop integrating process, not just a simple, simple rate up, simple rate down. Can the software handle, a closed loop step change? Can it change automatic, and can it handle those tunings for an integrating process? Then, can it handle non-steady state self-regulating processes? So that's usually not a claim that other software packages will make, because they don't have that. There's not a way to get a manual test that looks non-steady. So can it handle that? And then, for the gold standard, right? Can it just handle full-on oscillatory data to get fed into this model filter? Can it deal with it? Can it give you the numbers you need without you needing to baby it in a variety of different ways? Dennis?
Great remarks there, Brett. And thanks for summarizing. Control Station has been in the business of developing PID control tuning software since the late 80s. And based on our experience, we've compiled a list of features that practitioners regularly request. We're going to show some of those here on the screen. While it's key to have the ability to handle non-steady state conditions of integrating loops, it's also key that software support both live and historical data. That's a common need in industrial application. Like integrating, the ability to accurately model non-integrating loops is just as important, along with the ability to support multi-loop applications. Think of Cascade. Also, the availability of statistical data can be key to effective decision making while tuning PID control loops. Other functions, such as alerting users to issues with data and/or modeling, can be key to avoiding bad decisions while tuning. So too is the simulation of recommended tunings, so that you can contrast existing versus recommended tuning performance before implementing. Lastly, from our list, capabilities such as keeping a log of past tuning sessions, as well as generating detailed reports, can help users to understand how dynamic behavior changes over time and how they may need to address variability issues using methods aside or approaches aside from PID tuning. So here we are with a quick summary of today's webinar. We started with the premise that the advent of PID tuning software was to make the process of tuning control loops simple. First by automating the process and by standardizing those repeatable tasks, but also by performing the difficult function of modeling highly dynamic process conditions. That was the purpose of PID tuning software. Since the beginning of PID tuning software in the marketplace, nearly all commercial tuning tools have failed the customer's requirements. And that's because they force users to, in Brett's terminology, quiet a process before the software will actually work. And it's our belief that that's counterintuitive. With the introduction of non-steady state modeling innovation back in 2009, certain software vendors, including Control Station, we've claimed the ability to model non-steady state. But with the exception of Control Station, we believe that that is simply a misleading claim. When you buy software for loop tuning, it should work in open loop just as well as it does in closed loop. It should support all variety of processes, integrating and non-integrating. And especially the software should work when the user needs it most, when he or she is using it with everyday real world applications, which are typically highly noisy, highly oscillatory. So with those final remarks, Michelle, would you care to bring us home?
Happily. All right, Dennis, Brett, thank you so much. That was amazing information. So right now, we would like to have you put your questions in the questions box. I got some experts here, so please feel free to ask anything. Just go to your toolbar, click on the questions box, click on Open Pane, and you can type in the questions. We have one question here that I'm going to read. Dennis, can you go to the next slide while I do that? All right, the question here, does your class, Techniques for Applied Process Control, teach users how to mitigate all the issues you have presented today? Dennis, I think this is for you, yes?
Sure, I'll be happy to take that one. Yes, in fact, it does prepare practitioners to address the issues that are covered today, though it's important, it's essential to note that the Techniques for Applied Process Control course is a theory-based course. It's not how to use our software, but rather it is providing an understanding of dynamic process behavior and the fundamental elements of the PID controller, such that you as a user of software can make informed decisions, that you can test what the software may be telling you and feel confident that what recommendations are made will actually allow you to improve control. But maybe equally important is the workshops are hands-on, and they're designed to teach practitioners how to model and tune dynamic behavior manually, so they can attack their variable conditions and make meaningful improvement. So it's both the understanding of the PID and how the proportional, integral, and derivative terms interact to enable improved control, but it's also a background with which practitioners can test the information from their software to make sure that it is actually going to achieve the desired end goal of improved and more stable production.
Okay, Dennis, along with that last question, there was another question related. Is Loop Pro Tuner mentioned or used in the class?
Brett, do you want to take that one?
Sure, yes. It is used in the class, maybe starting about a third of the way in. So we take great care to separate the instruction of loop tuning from the usage of the tool, but there just gets to be a point where you want to speed up the minutia of loop tuning, because we're talking about more advanced topics such as feed forward control, cascade control, and things of that nature. And if we were still manually tuning all these loops that we needed to deal with, it would be a waste of time, and it would be very frustrating. So we spend the beginning of the class introducing these manual techniques so that you can really understand what's going on, and then we bring in the tool to speed up those sections as we do other other instruction on other topics. But as I said, great care is taken to make it being a class of control, not a class of the software. We have a separate training class for how to use the software if you've purchased it. So we try to make this a separate class. So yes, the short answer is yes, it's used to speed up certain sections.
Okay, Thanks, Brett. So on your screen, you will see our QR code to our website. If you would like to check out any industry-related articles, success stories, sign up for training that we've been talking about this morning. Also, any future webinars. Our next webinar is September 26th, and this is going to be actually a fun one. It's a panel discussion, and the topic is the habits of a systems thinker. So I'll have 3 experts in the field that will address that topic. Next slide, please. All right, so we're going to do one final question for everyone today. I'm going to launch this. And while you're responding, I'll read the next question. Please tell someone from control station, provide me with more information on tuning, oscillatory noise, controllers, detecting negative trends that undermine plant performance, training events, shrinking lifecycle solutions, and tuning more than 100 control loops. So here we go. Next question. Are there different bump tests for non-steady state control systems?
So not really. So that's the benefit of the non-steady state, is that data is data. So we don't have a specific test that we require that you perform. We want to see dynamic information. That last slide that we had, that was the one I was so proud of. You could see that it was a relatively small set point change. And we were still able to get the data that we needed. But the set point, the bump test that you do, be it non-steady state or steady state, is going to be dictated by the limitation of the process. So you're going to want to do a test in the region where the process is operating. You're going to want to do a test that is safe. Right, you don't want to bump the process into a location that's dangerous. Perhaps you're operating very close to a constraint. You want to make sure you only go the other way. All of these tests are fine for the software. We just want to see dynamic data. But whether it's steady state or non-steady state is kind of independent of the type of bump test that you do. That's one of the benefits of the software, right? Is that non-steady state? It doesn't even care. It's just data one way or the other.
Okay, thanks, Brett. All right, I have closed the last poll. Can we go to the next slide, please? All right, if you would like further information, we have process control specialists available to you. Brian and Alessia are in North America, and then Damien and Kathy Sweet are in Europe, Middle East, and North Africa. Looks like we have time for one more question. What about oscillation due to mechanical issues? How does steady state affect that?
Got it. So I'm assuming that's something like valve stiction. So that's an interesting one. So there's 2 types of mechanical issues, right? One would be that the valve is kind of operating near the seat, so that there's just weirdness that happens with dynamics in that situation when the valve's like 1% open, 2% open. Those are fine. There's this non-linearity in the process that is causing the process to just behave in an oscillatory fashion. There's no issues there. The software can handle that. If it's valve stiction, so valve stiction, for those of you who aren't familiar, is where there's something maybe gumming up the actuator, and so the controller is asking, the valve isn't moving, asking, and then all of a sudden it jumps all at once. Now it's too far in the other direction, and so then the controller is asking to close, and it kind of is jumping back and forth. So that type of mechanical issue needs to be corrected before anything gets fixed. You can't tune away a stiction problem. You can make it slower, you can do certain things, you can kind of work around it, but you can't fix the oscillations due to stiction. So what's interesting, right? So part of the, Dennis mentioned briefly, there's a statistics component in Tuner where you can analyze data to see whether the loop has stiction, right? So that's one thing you can do. Or also, I believe in the question that you just asked, there was the contact for 100 loops. So we have a product called Plant ESP that runs 24 hours a day that can also analyze stiction for all the control loops in the plant all at once. And so you can say, I need to go fix the oscillations in this loop. Oh, wait, it has stiction. I have to fix the valve first. Right, so that's kind of it. So depending on the mechanical issue, that can impact what you have to do, or whether you can tune it, or whether you have to fix an underlying issue first.
Okay, thanks, Brett. All right, I think unless there's another question, we are going to wrap up this webinar. Again, I will mention September 26th, our panel discussion on the systems thinker. Please sign up early. There's only so many seats available. Other than that, I would like a special thanks to Dennis and Brett for some amazing information today. Dennis, Brett.
Thank you,
Yeah,
Michelle.
thanks. Thanks for your time,
Thank you, everybody, for joining us.
All right. We will see you in a couple weeks, everyone. Thank you for the privilege of your time today.
Bye, everybody.
Bye-bye, everybody. Thank you.